All right, guys, so here is our video for class today. Sorry about it, but the weather makes my internet really spotty, and I had to cancel my earlier class because I could only hear every other word from my students. So here it is. We are starting this week in acids and bases. So I want you guys to take a minute before we get started to think about what comes to mind when you hear the word acid and what comes to mind when you hear the word basic, right? So we all come in with background knowledge for these two terms. I know when I say acid, you guys think to green liquid that just dissolves and eats away and makes everything that goes into it disappear. Right? That's normally what we think about with acids. When in reality, the term acid is a lot more broad, and it's not necessarily that awesome, corrosive stuff that we think about. Granted, there are acids that do eat away and dissolve away, very strong acids. But we also have weaker acids. And even strong acids can have a middle-of-the-road pH, right? It just depends on the chemistry, and that's what we're going to be learning about in this chapter. How to recognize chemically what an acid is and what a base is, and to understand the reaction between an acid and a base. We're also going to be looking at water, because water is a cool compound that can behave like an acid sometimes and like a base sometimes, depending on the situation, and kind of look at that. So we are going to get started, and the first part of this chapter talks about the properties of acids and bases. So let's take a minute and let me figure out how to flip my camera. Alrighty, so we are going to create a chart that compares and contrasts these acids and bases and their basic properties. So, acids, you can see there's a picture of a lemon here because lemons and oranges and other citrus fruits are a very great representation of an acid, right? Because if you bite into a lemon, how does it taste? It tastes sour and makes you pucker your lips, right? Have you guys seen there's a TikTok going around with like a lemon challenge with babies where parents give their babies a slice of lemon and watch their reaction? Because it's got a really strong sour taste. That's because of the acid content in that lemon. Oranges are the same way, right? So our acids in general taste sour. They make you pucker your lips. And then another example of that would be like Sour Patch Kids. I love sour candy, and the little crystals on the outside of the Sour Patch Kids, that's all just acid, right? That's why candies and sweets like that aren't good for your teeth, because they actually dissolve away the enamel on your teeth. But anyway, brush your teeth after you eat candy, guys. So our acids also have this really cool property. They turn litmus paper red. So litmus paper is an indicator species. So your book talks about that. Indicators are just substances that change color when they're in the presence of an acid or a base. So they change color based on pH. We have a wide range of indicators. Litmus is probably the most common because it's one of the cheapest. And we'll see that in a minute. I have a good simulation with that for us. So acids react with metals to make hydrogen gas. That's why we typically think of acids being corrosive, because we put metal in them and the metal disappears because the acid eats it away, right? Really, that's just a chemical reaction there that's taking that solid metal and turning it into aqueous ions and releasing all the other stuff as gas. Acids also react with carbonates to make CO2. So those are acids. Opposed to that in almost every way are bases. So while acids taste sour, bases taste bitter, right? If you've ever had your mouth cleaned out with soap, you understand that bases are bitter, right? And they turn red, they turn our litmus paper blue. So they're the opposite of our acids. And instead of kind of burning, they feel slippery to the touch, right? So instead of being kind of abrasive like we would think about an acid, they are slippery. They also do a much better job at eating or corroding fat, right? That's why our soap and cleaning solutions all tend to be basic, because they dissolve away. That's how they clean, right? Think about Dawn dish soap and grease, right? That Dawn dish soap cuts the grease, dissolves it away, or corrodes it, reacts with it, and we're left with a clean surface. If you guys have ever been to a hotel and you've used a little hotel soap, typically that soap's pretty cheap, so it doesn't have all the nice little additives in it like our nice soap that you purchase that's a little more expensive. So normally after you use that soap, your skin feels real dry. That's because that soap has dissolved away the entire outer layer of your skin and all those natural oils that your skin has on it in an effort to clean you, right? So soap is our picture for something that is basic, right? Let's take a look at the chemistry of an acid and a base. So we want to look at the chemical definition. Now these are just properties, right? They're not necessarily chemical structures or that. So now we're going to move into looking at actually chemically, what is the definition of an acid and a base? And it's important to note too that scientists can't really agree on the definition of an acid or a base. There are several schools of thought. If you study chemistry in college, you'll learn about those more in depth. Though the definition we're going to focus the most in the scope of this course is the most broad. It's our Bronsted-Lowry definition of an acid and a base. So we're going to be focusing on this idea that acids donate a hydrogen ion and bases accept that hydrogen ion, right? So we've got water here. And water is a cool substance because it is amphoteric. So that means that it can be both an acid and a base. So let's look at this picture here. And we see the red and the blue. That has to do with the indicators, right? So sorry. Acids typically are red. They turn litmus paper red. That shows they're acidic, and bases are blue. So we see our little particles up here. Our red one is going to be the acid one, and our base one is going to be the blue one. So if we look at it here, acids typically have a hydrogen ion, and bases typically have an hydroxide ion. That's not always the case. There are things that behave as acids and bases that don't have a hydroxide ion, but that's beyond the scope of this course. So here is another good picture of the chemical definition of an acid and a base. Now there are some terms in here that you're not necessarily going to have to know, but it's important to know that these things occur in pairs, right? So you can, whatever is made after an acid loses its H plus is typically called our conjugate base, and whatever is made after our base donates, accepts that hydrogen plus is called our conjugate acid. So the base becomes an acid, the acid becomes a base. It's kind of like this giant pairing, right? So we want to be able to kind of pick out what is going to act as an acid and what is going to act as a base. So we're looking at the before here. So we're comparing the before and the after. So if something loses a hydrogen, it is going to act as an acid. So we see this red, our little water molecule over here, the oxygen in the middle, and at the end, we've lost one of the little white pieces. That is a hydrogen ion. So we are down a hydrogen ion. It donated that to the solution, acting as an acid. Our base is different. If we look, before it has 3 hydrogens, and after it has 4. So it accepted that hydrogen ion from our acid. Therefore, it is acting as a base. And NH3 is actually, if we look at it, it is always going to be our covalent base. It's one of the only things that are only compounds that you'll have to learn about that is a base that does not have hydroxide in it. So it's one of the good ones to memorize. So NH3 becomes NH4 plus. So that is the acidic form of NH3. Okay, so acids, what's important for us to know from this picture is that acids lose a hydrogen ion or donate a hydrogen ion, and bases accept that hydrogen ion. That's the definition of an acid and a base that we're going to camp out and learn on in this course. So I have some examples for us, and your book has a couple of concept check questions where you're trying to identify the acid and the base species. So let's look at an example. Now this example that I'm going to show you is a lot more complicated than the ones in your book. but I feel like it's best for us to look at the more complicated ones, because then you'll be able to do the easier ones. Okay, so here is our question. We want to identify the reactant, acid, and base in each of our following reactions. So these reactions are an acid and a base reaction, right? So we want to be able to pick out the thing that is going to donate the hydrogen ion and pick out the thing that is going to accept the hydrogen ion. So if we look right here, let's make sure. So if you look right here, we have got this weird substance that's got NH3. Go back in. NH3 plus and H3C. So this little line right there, that little stick, is just showing that these things are connected. And then we've got an O negative that's stuck to a CH3, and that is producing, after it reacts, H3C and H2, and OH stuck with the CH3. So it's going to take you a hot minute to be able to see it, but once you see and can follow the hydrogen ions, picking out the acid and the base is easy. So remember, our definition of acid and base has to do with the hydrogen moving, right? So we want to find the species that loses a hydrogen ion. That one is going to be our acid. And we're going to find the species that has an extra hydrogen at the end. That one's going to be our base. Because remember, bases accept, acids donate. A hydrogen, or some definitions of acid mean it's a proton donor. Because it's an H plus, that's really just a proton, right? So let's look. So this guy is going to pair with the one that has the NH in it. So that's going to be this one. So this would be our pair, A and C. So we want to look at how A changes into C, what happens to its hydrogen, or other things, right? So the H3C hasn't changed, but the N over here has lost its positive charge, and it has lost a hydrogen. It's got 2 over here and 1. So it donated one of its hydrogens. So does that mean it's the acid, or does that mean it's the base? Hopefully you're seeing that it is acting as our acid because it is donating a hydrogen. It's losing one. It's giving it away to something else. So our acid would be A. Our base then, let's prove it to ourselves, would be this thing. So this thing starts out with a O over here is negative with a CH3, and let's look at how it changes. Oh, we lost its negative charge. It accepted that H plus, and now it's neutral over here, and it's got this OH. So this species has accepted a hydrogen ion, and therefore is acting as our base, right? Let's look at the next one. We've got HCl plus sodium cyanide, Na plus and Cn minus. So these are ions that are stuck together as an ionic salt. So we've got HCl, and we're told that it makes sodium chloride, Na plus and Cl minus. So that's a covalent ionic compound, and HCN. Okay, so let's look and see if we can see where our hydrogen went. So over here, the hydrogen, our hydrogen is stuck with the chlorine. And over here, the chlorine is all by itself. So this substance lost a hydrogen, so it donated a hydrogen ion. It is acting as our acid. And I'll give you a clue, your book does too. Anytime we see a covalent compound that has an H at the very beginning, that H is going to be an acidic hydrogen. So that H is going to be an H plus. That substance will almost always act as an acid, right? This one has 1 H, so it can donate 1 hydrogen ion. And if we see over here, let's see if we can find the species that is going to accept that hydrogen ion. So it went over here to the Cn. So that means that this ionic substance, this salt, is going to act as my base, right? So here, I guess if we're looking specifically at this, our cyanide, the Cn polyatomic ion, is going to act as our base, right? So the more of these you practice, the better at it you're going to get, and the more you're going to see like a chemist and be able to pick out our acids and our bases. Right, so don't give up, don't get frustrated. It just takes some practice. And we'll see this in lab. We're gonna do an acid and a base reaction and collect the gas. And then use our gas laws to figure out what the acid and the base reaction was. So it should be a pretty fun lab where we're gonna be applying this concept of acids and bases and the gas laws from last chapter. The questions in your book are a lot easier than these. These are a little more complicated. So if you could follow with me through these, the ones in your book should be no problem. Now, let's go back and let's look at our simulation. So this simulation is going to show for us a couple of things. So we're going to be looking at water here. Water, like I said, was amphoteric. That means that it can behave as an acid or a base. And we see that because over here, we're producing something that has accepted a hydrogen ion. So to produce this, our water acted as a base. Or I'm sorry. It gave away, yeah, our water acted as an acid. And to produce this one, our water acted as a base. It accepted a hydrogen ion, right? So, from the OH. Yeah, so water can act as both an acid and a base. And you can see up here, this would be like our OH. This would be our hydronium. That's what you call H3O plus. And it just shows that that's an acid, right? So we can look at what it means for an acid to be strong or for an acid to be weak, or a base to be strong or a base to be weak. So a strong acid, we can see in here, just means that our acid has disassociated. So we talked about that word before, disassociate. And when something disassociates, it breaks apart. So a strong acid is going to donate more hydrogen ions or more hydrogens than not. Our weak acid likes to stay an acid. It doesn't donate its hydrogens as much as a strong one. So the strength or weakness of an acid or a base is not in how corrosive it is or how much it dissolves a fat. Our strength of an acid has more to do with how many hydrogen ions it donates or how many it accepts, right? So that's the biggest misconception here when we're talking about the strength of acids and bases. It's not in their physical ability to dissolve stuff and break stuff and corrode stuff. It's more so in how much of that acid at any given time has broken apart into its, has broken up and donated or accepted its hydrogen ions. This over here, if we look at our tool, this is the litmus paper. So you can see up here, litmus paper has a color code to it. So all of these different colors indicate something special about that pH. A pH is just a measure of ion content. So something that is a very strong acid will donate a whole bunch of hydrogen ions and will have a low pH. So we get these red colors, right? Our bases accept a hydrogen ion, right? And make most of the time hydroxide. And as a result, we'll have a very high number for their pH. So bases have a low pH. I'm sorry, I said that backwards. Acids have a low pH and bases have a very high pH, right? So we can dip our indicator in here and we see it's orange, right? That tells us that our pH is somewhere in the 4 to 6 range, right? So that means that this is a pretty weak acid. That acid has not broken apart completely and we aren't left with fully hydrogen ions. We're somewhere in the middle. Some of that acid has not ionized and has not donated its hydrogen. Let's see what happens if we pick the strong acid, right? So we've got way more of our leftover, whatever's left after the acid donates its H+, the negative ion there. So we're going to dip it in and ooh, we see that dark red color. So its pH is closer to 0 because most of that acid has disassociated and donated its hydrogen ions. And we see the same pattern if we play around with this for bases. So here's our base. This is a strong base. So most of the base has broken apart into its ions. It's accepted its hydrogen. And we do it in here, and it's got a very high pH, right? It's like 12 or 13. In our weak base, we would predict has a more middle of the road pH. Yep, so it's got like a 9 or a 10. Our 7 is considered our neutral pH, so that means it's neither acidic nor basic. There's not many hydrogen ions that are free floating, and not many hydrogen ions that have been bound and accepted by the base. So pH is what 7 is considered neutral. Okay, so let's get out of this and let's look at an actual solution. So we're going to look at concentration. So this is our little pH meter, and we're just going to play around with this, right? So we've got an acidic solution now. Let me move this little bar over, and I want you to see how the colors change on the inside. So remember, we've got a strong acid, which is like our HA, and we're combining it with water. And it's going to break apart into the A minus, so this would be the leftover acid after the H has been donated. Our water here is going to be the acceptor of that hydrogen ion and make hydronium. So our water here is acting as the base. This would be our acid. Right now, it's a pretty weak acid, right? Our pH is 4.5. So I'm going to make this acid stronger, and I want you guys to look at what happens to the color. So we're seeing more of that water allowing our HA to ionize and dissociate. And what's happening to the pH? Our pH is getting lower and lower and lower and lower. And now this is a strong acid. Almost all of that initial acid has broken apart and donated its hydrogen. Lots of water has accepted that hydrogen, and that means our pH has gone down because there are more hydrogen ions in this solution than they were when it was weak. Okay, now let's look at a base. Let's see it. So this is a very strong base. It's got a pH of 12. I see that most of my base has turned into BH+. Most of it has accepted a hydrogen ion from the water because the water is acting as our acid in this instance because it's with the base. So let's see what happens when we make this base weaker. We should see more little grays pop and our colors disappear. So this is showing us that a weak base is less likely to interact with the water and accept a hydrogen ion from that water, right? And we have a pH that is closer to neutral, right? There's not many bases that have accepted the hydrogen ion from water. So when we're looking at these acids and bases reactions, we're going to be calculating pH and looking at that math here later on in this chapter. But for the first part and for most of this week, we just want to look at what happens when acids and bases react. Where does our hydrogen go? How can we predict what's an acid and what's a base? And looking at that. So now, when acids and bases react, there's a pretty good prediction that we can do there. So acids and bases react. So the next important part we got to talk about is that when an acid reacts with a base, we have what's called a neutralization reaction. So our acids have a very low pH, bases have a very high pH, and this magic thing happens when we mix them together. You can even see the colors there. Our pH gets neutralized. That's why it's called a neutralization reaction. And we're left with water and a salt, right? Because if we saw from earlier, acids and bases have these positive and negative ions in them that are kind of left over when our hydrogen leaves, right? Or when it's accepted. So these opposing ions are going to be that are left over when our hydrogen leaves or goes to where it needs to go. We've got these positive and negative charged particles that are left over floating in the solution, and they're going to be attracted to each other and form a salt, right? And that salt is not just sodium chloride, right? That's any ionic substance that's left over there. So now we're going to look at a couple of examples of this neutralization reaction and see how we can predict what's going to happen when an acid and a base neutralize. Okay, we want to be able to write a balanced chemical equation for the reaction between hydrochloric acid and sodium hydroxide, right? So looking at this, how can I pick out what is going to donate a hydrogen ion and what is going to accept it, right? So looking at this, I see my H in front of the Cl. So HCl, this H is at the front. That means that this one is almost always going to be my acid. So it is going to lose its H plus. This one has to be my base because I'm told this is an acid and a base reaction. So it is going to accept an H plus, right? So what is that going to form, right? We can look at this in a different way, right? We can actually disassociate this because that's what ions do when they're in a solution and they are what acids and bases do. They have to ionize in order for this acid and base reaction to happen. So really, we have H plus and Cl minus, and we have Na plus OH minus, right? We can break these guys apart and see what their ions are going to be. So since this species is going to lose its H plus, this one is going to accept its H plus, but because of their charges, which piece over here is going to accept that H plus? The only one that can is the -1. So this plus is going to go with the negative ion, and it's going to leave its cation. That cation is going to be free. It's no longer going to be associated with this OH negative. So this one, the only thing that's left for it to bond with or be friends with is, if we look conveniently, the negative ion from our HCl, right? So we see how we can repair the positives and the negatives, right? So when H and OH come together, we get HOH, or it's another way to write H2O, plus our salt, NaCl. Now these things are tricky, right? This one was an easy one because our ions have a 1-to-1 ratio. But let's say we had an ion over here that had a 2+ charge, right? Then we would need lots of Cl. We'd have to write the correct chemical formula for that, right? So don't forget all the rules, all the things that we've learned, because there's a lot of chemistry that we've learned that goes into successfully completing a problem like this, right? So then we'd have to go through and make sure that our equation is balanced, right? With this being the beginning and this being the ending. Make sure that it's balanced, and then you've got your balanced chemical equation. I do want to take a second and work one of the concept check questions with you, just so you kind of get a little more comfortable with this. So we are going to work concept check question 6 together. Okay, for concept check question 6 here, we want to know what the balanced chemical reaction is when HClO3 and NH3 react. So looking at this, our first step is to pick out what is going to act as the acid and what is going to act as a base. We have several tools in our toolbox to do that. I look right here and I automatically see this H comes first, so that should ding, 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 ding. This one's probably going to be my acid, but let's make sure. Let's look at this one. So bases normally have OH in them, or I see NH3, ding, 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 ding. That's my covalent base. It's the one I should recognize, right? So we know that this guy is going to be our acid, and this one is going to be our base. So what does that mean for us chemically? This H is going to pop off. So this thing is going to disassociate. And since it's 1-to-1 ratio, I automatically know what the charge has to be on this. Since it lost an H plus, its charge has to be minus. Right, because when they went together, they were neutral, right? If I lost an H plus, the charge on that's got to be minus. Okay, so we've got those two. So this guy is my base, so it is going to accept this hydrogen ion, right? So this guy is going to go here. My NH3 is covalent, so that means it doesn't dissociate. There's no pluses and minuses. That's why NH3 is a different type of base than the ones that have OH in them. The bases that have hydroxide are all ionic and will also dissociate just like our acids. But this one is different. That's why I wanted to show it to you. So, since there are no charges here at the moment, when this guy accepts its hydrogen ion, what do you think is going to happen to its charges? Right? So, let's kind of look. This is going to be assumed into here, and that's going to make NH4. But what happens when a neutral thing accepts a positive charge? Its overall charge has to be conserved and will also be positive. There's no negative here right now to balance this out, so we're left with an abundance of positive charge. So this thing actually becomes an ion now, NH4. Or, if you remember from your polyatomic ion names, ammonium. Right? So we're left with, now that we've satisfied this, we know where it goes and what it makes. It makes ammonium, right? Now we're left with this ClO3, and it's got a negative charge. There's nothing else in this solution to stick with it, so we're just going to be left with it, ClO3 with a negative charge. I think it is chlorate. Might be perchlorate, so don't hold me to that. It's some form of chlorate. But anyways, so now your book stops here, but I want you guys to see. We have two polyatomic ions, one with a positive and one with a negative charge. So this substance is actually going to stick together and make NH4 ClO3, one thing, right? That's why this one is cool. So if we wanted to write a full chemical reaction there would be HClO3 plus NH3 make NH4ClO3. And then we have to go through, of course, and make sure that it's balanced. And I think this one is, because it's not a polyprotic acid. Cool. So hopefully that wasn't too difficult for you to follow. This is probably one of the most complicated ones. The ones that have ionic bases are a whole lot easier. The only tricky part is when you're making your salt at the end, making sure that you write the formula correctly because of your charges, right? This one was another easy one because our charges were equal and opposite. They will always be equal and opposite, so you've got to remember your formula writing for ionic substances rules, okay? I do want to say one more thing before we end, and that is about polyprotic and monoprotic, diprotic, polyprotic acids. So HCl, H2SO4, and I'm not sure what another one is, but something that has like H3. Maybe I think H3F is one, hydrofluoric acid. If we look here, at these acids, this one can donate only one hydrogen ion. So when it breaks apart, it's got H plus and Cl minus. It is called monoprotic. Mono meaning one hydrogen ion for every other, every anion. This one, H2SO4, is what we call diprotic, meaning two. So if we were to disassociate this thing, we actually have two hydrogen ions and one sulfate. Right? So it's got two hydrogen ions. It's going to make our pH go down faster than this one because it's got twice the ions that it is pumping into that solution. And our pH is just a measure of the amount of hydrogen ions we have dissolved in that solution. Now, polyprotic acid is going to have more than one, right? Even more than two. So there are some insanely strong acids out there that have been made in the lab. But they just have, some multiple of hydrogen ions. So this one, if we were to break it down, it has 3 hydrogen ions for every one of those things that is one of those acids that's in that solution. So that's what it means when it says monoprotic, diprotic, triprotic. And that'll come into play, we'll see, as we start doing stoichiometry with these acids and bases to predict how much of an acid we need to neutralize a set amount of base. And that's where the math comes into play. So we'll be looking forward to that in lab on Thursday and in class next Tuesday. So I hope this helped explain acids and bases. if you had followed with me through class today, we've covered the vast majority of chapter 11 already, all the way to page 341. We even talked about the neutralization part, but not the math. So we should be prepared to dive into that the next time we're together. So hope you guys have a good rest of your day, and hopefully we'll see some sunshine before class next time. I'll see you guys later.